Welcome to module 28 of object oriented analysis and design. This module is the third and concluding part of our discussions on class diagrams as UML diagrams. So, in the earlier two modules, we have first studied the basics of class diagram, how do you represent class and how do you represent properties of a class, the operations of a class, how to control the visibility of different members, the properties and attributes, and how to specify different details behind these properties and operations, like if a property is read only, what if a property is derived, and so on. Then we started discussing about this was in the last module, discussing about the different relationships that may exist between two or more classes. And we observed that there are a variety of relationships spanning association, which basically relates two or more classes in a certain way, and in any generic form a relationship can be viewed first as an association, which has two ends that can be qualified. There is a reading direction, there is navigability in the association, which basically specifies as to how does one class relate to another. Associations mostly are binary, but they could be ternary or n-ary in general. Then we take a look at different forms of aggregation. We had earlier seen two major aggregation structures possible amongst classes. One is of composition or component structure, where like a car has four wheels. So, wheels are composite the car. So, this is has a relationship which is in class diagram modeled as strong aggregation. And we also saw a weaker version of the aggregation, where you have a certain class has one or more objects of some other class related to it, associated to it to complete the functionality. Library has multiple users who use the library, but they really do not, they are not really contained within the class in the sense of composition. So, we designate them as weak aggregation. And we have seen for association, weak aggregation as well as strong aggregation, what are the notational details, the multiplicities, the empty and filled diamonds and all that. So, in view of the in continuation of that, we will discuss three other kinds of relationships: the generalization, the dependency, and the constraint. These are further relationships that may exist between two or more classes. Besides that, in this module we will also quickly take a look into our running example of LMS and try to improve on the class diagram of LMS that we have been constructing so far. So, first we start discussing about generalization. I would like to remind you regarding what we had talked of in terms of generalization several times earlier. So, it is a generalization specialization relationship between any two abstractions that are possible. So, when I say daisy is a flower, I have a daisy class or a daisy concept, I have a flower class, a flower concept, and by inheritance or generalization specialization, I mean that if daisy is a flower, then daisy has all the properties that the flower has, but daisy may have some more additional properties. We say flower is the generalization and daisy is the specialization, and we had seen, without actually formally introducing class diagram, we had seen their depiction in terms of a diagrammatic form. So, I would urge that before you go through further of this module, please refer to the earlier modules where inheritance and these relationships have been discussed, so that you can understand this in stronger detail. Particularly, you should look into the various flavors of inheritance that are possible. All of those flavors can be represented in terms of the class diagram. So, this is the basic representation of generalization. If I have should formally say, it is this is the generalized class and these are the specialized classes, and we draw an arrow from the specialized class to the generalized class, and the arrow head is an empty triangle, which represents that it is indeed is a relationship. So, we read it as checking account is a account like this, savings account is a account, credit account is a account. And with this, what in semantically it means that account has some properties and some behavior, some operations. For example, account will have a property in terms of holder's name, in terms of the account number, the account balance, and so on. So, being specializations, all of these specific types of accounts like checking account, savings account, or credit account. In Indian banking, we also have term deposit account, we have current account, and all those. They will certainly have all these properties, that is the holder, the number, account number, balance. But in addition, if I talk about specifically a savings account, then it will have certain further properties. Maybe savings account has a restriction that I must have a balance of say 1000 rupees at the minimum in the savings account, which may not be applicable in terms of a savings checking account. It may not have that property. Savings account may have that I can transact at most say 1 lakh rupees within a single day, but checking account may have unlimited options for transactions and so on. So, these are different specializations which use the properties that the generalized class has and adds further properties at their own level. So, this clearly makes the depiction of the reality of the real world. So, that whenever possible we would like to work with the generalized concept, and this will certainly enhance the understandability as well as the reusability of the design. Now, in terms of the diagram representation, you can see that we have 3 specialized classes of one generalized class, and we can draw 3 separate arrows. If we do that, then we say it is the drawing is in terms of a separate target style, or we could draw a common bar line and let all of these specialized classes hang from there, and this bar in turn actually points to the generalized class. This is called a shared target style. Now, in class UML class diagram, both these styles are available. Depending on the context, depending on what is easier to draw and represent, you could choose any one of them from time to time. Naturally, in terms of inheritance, you can have multiple inheritance. This is again a slide from module 14, where we had shown that one bank account, this is a specialized class. This is specialized from interest bearing item, asset, as well as insurable item. So, it says that the interest bearing item has the property that I can earn interest on the deposit that I have. Bank account has that property, bank account allows us to do that. So, we have a specialization on this. Similarly, the asset is having certain fund value which you can pledge to somebody or which you can use to take loan and so on. So, bank account can be used for that purpose with the balance that I have. So, bank account is also an asset. So, here we see that a same class is a specialization of more than one classes. Whenever that situation happens, then we say that we have a situation for multiple inheritance, and as this example shows that you could have multiple inheritance from 2 or more classes. Here bank account has 2 generalizations, security bank account has 3 generalizations, whereas security has just 2 generalizations and so on. So, certainly we can represent multiple inheritance exactly using the same notation as the single inheritance. So, we can see here that director is a manager, manager is an employee, and we have consultant manager and permanent manager. The consultant manager is a manager on one side and is consultant on the other. So, it gets both these properties. So, being a manager, it will get the rights of the manager, being a consultant, it will get the flexibilities that a consultant gets. Possibly it is not full time, he possibly gets paid according to how much he has worked and so on. On the other hand, there could be permanent managers who are managers, again get the same manager rights, but is a permanent employee. So, the permanent manager also inherits the permanent employees benefits like retirement benefits, like leave, like a fixed salary and so on. So, multiple inheritance is a very important feature which is often used in modeling different real life scenarios and plays a critical role in terms of the class diagrams. Now, one point that I would like to highlight is the multiple inheritance as such is implicitly allowed by the UML standard, in the sense that since you can draw from one specialized class, you can draw multiple easy relationship arrows to other classes. So, the multiple inheritance gets represented in a class diagram. But as such, the standard has not tried to provide any specific definition that if I have multiple inheritance, and this is what the inheritance would mean. Particularly, there are certain critical situations, like if I have a class like this and I have two classes specialized from that, this is fine, but then I have one class which multiply inherits from these two classes. I have A, B, C and D. So, D multiply inherits from B and C both, but B in turn is a specialization of A, C in turn is a specialization of A. The question is, certainly if I use the transitivity of the inheritance, that is transitivity means director is a manager, one generalization, manager is an employee, the other generalization. So, there is an implicit transitive inheritance between the director and the employee, that is director has inherited all the properties of an employee through the manager. So, if I use that logic here, then D actually inherits the properties of A through B, as well as D inherits the properties of A through C. Now, does it mean that some of the properties will be inherited twice? Some of the operations may have been redefined in B, may have been redefined in C. Then what will happen to those operations? How will D interpret those operations, because it could inherit the same operation from B and C, because they existed in A, the original root class, but it may be inherited in two different forms. So, what should D do in terms of defining its own operations, own properties? So, there are issues in terms of how the multiple inheritance should be interpreted, and you should keep in mind that while it is implicitly allowed, standard has not provided any specific definition for that. So, you will find that a multiple inheritance model as created in UML class diagram, when you try to take it to the OOP, an object oriented programming language like say C++, then specific OOP language will have specific interpretation, specific semantics for multiple inheritance. So, you will further have to understand what is the semantics of the for multiple inheritance for a specific language, and then use that in the implementation model. So, some care is required to actually model with multiple inheritance and then take it forward in terms of building up certain actual implementations. Another form of relationship that is possible is known as dependency. Dependency is somewhat represents a little bit of a different concept. It just says that between two classes, this one class depends on another, one class is affected by another, one class may be using another. So, unlike association, which tells you that specific messages are intended to be sent through association, or when we talk about aggregation, we are basically talking about strong or weak compositional aspects of the model, or when we are talking about generalization, we are certainly talking about a very strong structural similarity between the classes. In dependency, we more or less just try to highlight that how does one class may be affecting another or may be dependent on another, and that is typically drawn with dotted arrow at the arrowhead at the end, and depicts that this class on the left requires the other class or depends on the other class. Yet another form of relationship could be expressed in terms of constraints. So, constraints, for example, let us say there are two forms that we have shown here. So, we are saying there is a class stock and there is a class vendor. So, basically it is a scenario of procurement. So, stock is the inventory and vendor is a provider from whom we can buy and build up the stock, build up the inventory. So, we have association purchased from, the direction, reading direction is not shown. It is clear from the way it is written. So, the reading direction is like this. The multiplicities are anything. So, any item can be purchased from any vendor, you may not purchase from anybody also. Given this, we need to also specify that, well, we will not purchase from actually any vendor available in the country. We want to purchase only from the vendors who are listed in the National Stock Exchange. So, we represent that by with a dotted line, and this is kind of, these are typically called notes. I am sorry, let me write it again. These are typically called notes with this corner cut. So, this kind of a note attached here, which say that well, in this relationship the vendor may actually contain several vendors who are not listed in NSE. They may be related to other classes in the system, and for that reason they may be there. But for this particular relationship, the vendor would need to be listed in NSE. So, you are putting some kind of a restriction, some kind of a constraint on that. Similarly, let us say we have a regulated water cooler. So, it is a regulated water cooler, means it is a water cooler which tries to set a certain temperature and maintain that. So, internally it will have a heater and a cooler. If the temperature has to go up, the heater has to be put on. If the temperature has to go down, the cooler has to be. So, to represent that, we have a association showing activates. So, this activates relation is applicable for the heater as well as for the cooler. But the reality of the situation would be that you would never conceive that you have a state of the regulated water cooler where both the heater as well as the cooler is working. You can conceive of this in terms of particularly car air conditioning. Our room air conditioners usually do not have the heater part, unless you are in a precision air conditioning system. But in a car air conditioning, you will always find that there is a dial like this which can be rotated, and it shows. So, there is a blue part usually on this end, and there is a red part usually on this end. The blue part designates that you are cooling, the red part designates that you are heating. Obviously, you will not do both of them together. So, how do you represent that in the class diagram? So, one provision is you have an XOR relationship, exclusive OR, which means that the heater heater activates regulated water cooler is valid, cooler activates regulated water cooler is valid, but both cannot be valid at the same time. So, it is exclusive OR, XOR is exclusive OR. Usually our OR means inclusive, or it could be either this or both, but exclusive OR means that both cannot happen. So, these are the different forms of constraints. For example, I could have another constraint, say let us say I have a person and let us say I have a committee. So, it is basically we are forming a committee from a group of persons. Naturally, the association could be something like participation, right. Say I can have star, that is any person, number of persons can participate in any number of committees. Then every committee needs a chairman. So, I can model that again I have a committee, I have a chairman. So, my relationship is chairman. Naturally, I would expect that every committee has one chairman, and a person could be chairman of any number of committees, including a person may not be a chairman at all. Now, if I just model it like this, then it will be quite possible that if I have a committee C and I have persons P 1, P 2, P 3, I have another committee, say 2 committees C 1 and C 2. Let us say that the participation is like this. He participates here and they say participate here. Now, can I have P 1 as chairman of C 2? Can I have, that is, if I say my blue is the chairman link, can this association be possible? P 1 is a chairman of C 2. Now, that would be absurd, right? This person does not participate in the committee, but how can he chair that committee? So, this infeasibility have to be represented, and we again use constraint for doing that. For example, the way this can be denoted is we can join these two associations with a dotted link and write subset. So, this is a subset constraint which say that the chairman, the chairperson association has to be a subset of the participation association, which means that if there is a relation between a person and a committee as a chairman, then that combination, that doublet of the person and committee must be a member of the participation. So, this will be ruled out. So, if C 2 has to be chaired, it will have to be either P 2 or P 3. So, if I say that this is what I have, P 3 is the chairman of C 2, then that will be valid, but P 1 being the chairman of C 2 is not valid. So, in this way different forms of constraints will have to be considered, so that we can model the reality in a more precise manner. So, this is just taking a look into the library domain model. We had earlier looked at this in terms of the let me go back to red, in terms of the properties. Now, we can see the various kinds of other relationship. For example, we can see a generalization relationship here, a book item is a book. We can see different, this is says the librarian manages the library, librarian searches the library, a patron here means a user, searches the library. So, these are like this search, manage, these are like interface classes, which basically give you different operations that you can do as a part of that class. So, how does a patron relate to the search interface is through this users dependency. So, there is a use dependency between. So, the patron needs to use the search interface to be able to perform the search activity. So, this is how all this can be done. These we have already seen, these are the different associations. This is a weak aggregation, strong aggregation, I am sorry, yes, weak aggregation, this is a strong aggregation and so on. So, these are all the different types of relations that you can have. And you can use this particular, the same example here it is annotated. So, you can clearly see the different kind of usage dependencies, interface realization, which is another kind of dependency and so on. Now, so that is all about the relationships amongst class diagrams. So, we can quickly go back to our leave management system and try to advance the class diagram, the UML diagram for the leave management system by a little bit more. So, I just pick up the use case diagram we had done in module 25. So, we know that these are the different actors we have already identified. So, naturally they will transform themselves into classes in the design, in the class diagram design. And we have several different types of use cases of how we use, and what is not explicit in the use case diagram is certainly all of these or a majority of these use cases need some other abstraction which is of leave, because when we apply for leave, when we request for leave, or when we approve leave, we need that abstraction. So, now we will see how we get those in terms of a consolidated class diagram. So, in terms of the class diagram, the tasks are to identify classes. Often you start with identifying abstract class, identify the properties and operations, identify the relationships, and finally combine them all together in terms of the class diagram. So, these are tasks which we have been performing all through the past several modules, and so we can just quickly glance through the result of that. Certainly, in the notation of class diagram, or main abstract classes, there would be many more, but main abstract classes are employee, which we say is an abstract class, leave is an abstract class, because we can see that there are several specializations of this which we have separately discussed earlier that will result. So, these are the two basic concepts. Beside that, there would be several other classes, like there would be a class for the leave store, there is a class for the documentation, there could be class for tertiary actors in the system, like doctors who prescribe different documentation and so on. So, with that we will try to complete the I will try to make a complete list of the identified classes. For the classes that we identify, we have different attributes, and we had seen the extraction of these earlier. So, for these abstract classes, we can add these attributes, these properties, and we can keep on adding more and more. These are I am not saying that these are the exhaustive list, I am just this is an indicative one which you can see how to put together. Then you on top of these attributes or properties, you have add different operations that the class do. So, we had started with out of this 3 compartments, we started first with this, which is the mandatory, the class identity, then the attributes or properties, then the methods or operations. So, this becomes a more complete class representation for the employee, as well as this one is for the leave. So, some of the associations again we had earlier identified: request, leave, report to. So, the different use cases you will often see, the different use cases actually manifest themselves as in terms of operations in classes, because the classes, different classes will have to actually provide that service to other objects, or they manifest actually in terms of different associations that exist between the classes, because that is how the classes interact. Then we have seen the generalization, specialization. So, in terms of the formal representation, this is what we have, the leave, abstract leave, and we had earlier shown this. We have personal or paid leave, we have post facto leave, uncertified leave, certified leave. All of these are basically abstracts, because the organization does not as such have something called a certified leave, or you cannot directly apply for a certified leave. What you apply for are at the leaf level, the different concrete class instances that are possible. So, this diagram now fits into our class diagram notation. So, if we put things together, and mind you, this is just a partial diagram, this is not a complete one. We will share the complete one as a solution of LMS. So, here you can see the actors have come into one hierarchy, which was originally captured in the use case diagram, but in addition to that, there is a association identified, which is report to. The executive reports to the lead with the multiplicity of 1 on the lead side and any on the executive side, which mean that many executives could report to a single lead, and it is possible that at a point of time a lead does not have any executive reporting to her. Similarly, the similar relationship exists, association exists between lead and manager. We could identify several others. Here we have the abstract leave class, and on this side as a whole we have this whole hierarchy, generalization hierarchy from the leave, which will all actually inherit the semantics of the association that the leave makes. So, critical is the employee abstraction and the leave abstraction say has a association requests, which is request leave. So, and which we want to mean that employee requests leave. So, employee has to initiate that and leave will get requested, has a multiplicity of 1 on this side and has a multiplicity of 0 to n, 0 dot dot n on the other side, because if you see that any leave will have an unique employee who has applied for it. So, on employee side the multiplicity is singular, but on the leave side an employee could request, may not request for any leave. So, the association could be vacuous or could request for 1 leave, 2 leave, different kinds of leave and so on. So, this has a multiplicity on here, and based on that it will reflect as we propagate down the relationship on the generalization hierarchy. This association on the generalization hierarchy will get different kinds of specialized form of this association, but the most fundamental is this association between the 2 abstract classes, another association of approval between the 2 abstract classes. And when we say this, you can see that between this approves and reports to, between these 2 association, you need to set some constraints. I have not done that, just left it open so that you could take it up and complete the diagram further, because certainly the leave of an employee is approved by another employee. That is because it is an abstraction. So, an executive is an employee, so a lead is also an employee. So, if you read it that way, then the approval basically means an employee is approving a leave which belongs to yet another employee. Now, certainly what you will need to rule out? You will need to rule out that in this approval process, it is possible that if the executive reports to the lead, only then the lead approves the leave for that executive. The executive will not approve leave for other, I am sorry, the lead will not approve leave for other executives who do not report to that particular lead. So, between whenever an approval has to happen, then that reporting relationship will also have to be valid. So, that sets a constraint. So, I will leave it, you discover more and more associations, aggregations and generalization, possibly generalization has been extensively done already, the constraints and so on, and try to complete this diagram. At a later point of time, we will come up with the solution also. So, this concludes our discussion on the class diagram as a UML diagram, and now you should be in a good position to be able to represent any systems prescription in terms of a class diagram. I would request that for the assignment management system, AMS system, you take it as your exercise to carry out the class diagram and get convinced that you are understanding all of those very well.